Good afternoon. Welcome to course Thermodynamics of Materials. We are considering the last example of construction of stability diagrams, sixth example, that is lead, tin and oxygen system. This was last day we advanced to some extent. This is the system involving lead, tin, liquid solution, lead oxide solid, tin dioxide solid, and the gas phase oxygen. So this will be the diagram. So what okay, this is, I have given you this diagram. I sketched last day, but today actually I have drawn it again for better sketch and label everything. So see what is the figure 6 stability diagram for the system lead, tin, oxygen, showing the stability fields of liquid lead, tin, liquid plus lead oxide. This one, liquid plus lead oxide. This is liquid lead, tin, liquid plus lead oxide, and then liquid plus tin dioxide. This one, and lead oxide solid plus tin dioxide solid mixture. This one, okay. This at a given temperature is a temperature. This is actually, we have considered 1023 Kelvin, 750 degrees centigrade. We will consider this. Actually, we will make an actual calculation this time and refer to a practical problem also. So let us start with the construction of the diagrams. Means main thing that we will do, we will try to find the equation of this curve AB curve. Okay, this is actually the boundary between liquid phase and liquid plus lead oxide. Then we find the equation for BC curve, that is the boundary between the liquid phase, that is lead tin alloy, and the liquid plus tin dioxide mixture. So this, and this is actually this is our job. This is our job. This here I tell you something. This is actually, to follow this, I have written some PO2. This is PO2 on the y-axis. This is PO2 versus Xn, mole fraction of tin plot. PO2 versus Xn plot, and temperature is fixed. As mentioned here, temperature is fixed. Remember, if you have not forgotten this, that is actually I think that you have not forgotten. So what is this? Why actually? Remember the beginning of this diagram, that is the beginning design is what? F max. Last day I did this, so it will be repetition, but still in short, F max, you want to know, is C minus P mean. Just I am repeating, minimum number of phase that you have to handle. So C minus P plus 2. C is actually, C is, this is a three component system, clearly seen. C, 3 minus minimum number of phases. You see, this is lead tin, 1 condensed phase, and this is actually liquid plus SnO2, means 2 phase mixture. This is 2 phase mixture, this is 2 phase mixture. So 1 condensed phase liquid is the minimum, but always gas phase is there, PO2. So on the y-axis, so liquid phase, minimum number of phases is 2. This liquid phase and the gas phase. So P minimum is 2. If you have put this, in fact we did this. This is actually something 2 plus 2 gives you what? Minimum phase C is 3, gives you 3. How will you, what is the significance of this? Remember, recall this. Okay, this actually I don't want to disturb here. And C3 is what? 3, fix 1, plot 2. Fix 1, so why shall I show? I write here, somewhere I write here. I write underneath here. When max is 3, it's better I show you here. Just for continuity. Just last day I discussed this is 3. So what you will do? Fix one to make it two-dimensional. Otherwise, it will be three-dimensional. Fix one and plot remaining two variables. Fix one. What is the temperature? Temperature is fixed. 1023 Kelvin. We have chosen plot 2. What you plot? PO2 versus XSN, mole fraction of tin in the lead tin alloy. That is actually this is the scheme. So remember this we should not forget. This is actually something we already discussed this last class, but repeated here for continuity. So we are all set. We have plotted now. Now this is actually the thing that you will be interested. Please take a note here. PO2 scale, y-axis. This is what I have. This curve is named AB, and the other one BC. They intersect at B. At B, actually, this X PO2 versus XSN variation of PO2 with XSN is for this region, for this liquid plus PBO, and the boundary that separates liquid plus PBO and liquid is given by AB, and the equation for this will be found out. And similarly, BC equation of BC will be found out. This is actually one thing, but I wanted to tell you that this is what is this? Yes, at B you see if you follow the AB BC for this part, AB for this part. At B you have two things equal, which are the value of PO2. See, PO2 changes for this curve. AB changes and reaches up here B, and this also changes and reaches B. So at B, PO2 for both the curves is same. Not only that, the value of XSN, x-axis, you see here also XSN changes, here also XSN changes, but at this point B, XSN is the same. This we will use actually. We will find the equation of the curve, then solve this actually finally, and we will actually try to find this value. This is very critical value. B has some practical applications, implications, industrial implication, softening of lead. This I will discuss. For the time being, you concentrate point A. Point A, I have actually, the PO2 value is 2.24 times 10 to the power minus 12 atmosphere. How we got this value? Remember, this is lead PB liquid and in equilibrium with lead oxide solid. PB liquid plus C here. This delta G0 is available on I write. Oh, I have written perhaps. Yes, I have written here. I have written today. Oh, very good. So this pen is now level. So this is minus 219. Oh, this value is given for this. So delta G0 from which you will be able to find PO2 equilibrium. Delta G0 will give you you see, and when PBO solid is pure and lead PB liquid is also pure, PB liquid pure. So this point refers to the coexistence of PB liquid and PBO solid. So PO2 corresponding PO2 obtained from this equation, and its value is 2.24 times 10 to the power minus 12 atmosphere. This is the in a sense oxygen potential, but PO2 equilibrium. So this value is easily obtained. This value. Similarly, this value, sorry, I have forgotten to mention, but I should write here. This is important. I should write here. This is important. I should write. This is for what? Tin and tin dioxide. This is the next one. So what is the PO2 equilibrium? Very easy, because they are with pure tin and pure tin dioxide. From the standard finality chain, you will get the PO2 equilibrium, and this value is 1.02. This is how I obtained this value. Okay, 1.02 times 10 to the power minus 19. Careful, atmosphere. So easy. So this is what? This is 10 to the power minus 12. This is much less. So 10 to the power minus 19. Right. This value. These are the values. And this equation of the curve is obtained. If obtained, then we will get the value of PO2 at B. This value will be 2.26 times 10 to the power minus 12. You may note that this value is not much different from this, but this actually we have to. This is the reality. This is what happens actually. So this in this small range of PO2, actually we have to work with this alloy, and we have to remove tin as much as possible. And when actually, and this corresponds, so this is the maximum extent of tin removal. This discussion I will take up later. So this is okay. So now we actually start here. Consider the two simultaneous equilibria, lead and lead liquid plus half O2 gas goes to lead oxide, and tin liquid plus O2 tin dioxide. These two, delta G01 is A plus Bt. Okay, work with the first one. Delta G01 is A plus Bt known quantities, and what is the known quantities are giving you the exact data, actual data. Is minus RTL and KT1. KT1 is found from this, since T is a known quantity. Yeah, so you can solve KT1, and KT1 has the expression activity of lead oxide over activity of lead liquid PO2 per half. So these are what? This value is what? I don't think this pains. So what is this? Now this is yes. This is 1. This is 1. What is activity of lead liquid? You consider this is representing this curve AB. This is the equation for AB. So AB what domain? This is lead enriched, and this is lead content of the liquid is large enough to be considered high concentration and to lie in the domain of high concentration, so that we can say activity composition curve or activity follows the Raoult's law. At high concentration, remember, solute obeys Henry's law, then solvent obeys Raoult's law, that is at high concentration. At high concentration, solvent, and then low concentration, that is solute. Solute obeys Henry's law. This recall this deal. So I'm telling you, I'm showing you. So this activity of lead liquid will be how much? It is X lead liquid, because that figure. Actually, last day I showed you. Remember, you have forgotten. This is the Raoult's law. At high, suppose this is the deviation. I tell you. Suppose this is the deviation. So let me draw this solid line. Okay. This is the deviation, and then XB, AB. Recall this. This I'm repeating. So 0, 1. When B here is a solute and there is a deviation from Raoult's law. This is Raoult's law. Raoult's law. Deviation is there. And Henry's law applicable such. Deviation gamma is there. Gamma still there. But as concentration of B increases and it becomes solvent at a very high concentration of that solvent, say it merges with the Raoult's law. So what is the meaning of Raoult's law? Raoult's law is AB is XP. So what is here? AB is gamma B XP. When there is deviation and when there is no deviation, AB is XP. So this happens. So it should be a large concentration, high concentration of B. Here lead is the component, the solvent, and tin is the solute. See, lead is the domain is 0.005 XSN. So this is pure lead, and between this domain we are working out the equation. So this domain is 0 to XPB is 0. Xtin is 0. This is Xtin is a pure lead. X lead is 1. Opposite. Xtin is 0. X lead is 1, 2, and this is Xtin. This is all Xtin. Xtin is 0.005 means what is X lead? 0.995. So it is close to 1. Large value, close to 1 also. So almost to close to. So what you will write? Activity of lead liquid, you can write XPB lead. Or you get what? Or you continue. What is X lead liquid is what? Since XSN is the chosen x-axis, so convert into XSN. So what it is this? You better maintain this. Sorry, actually. So what you can write this? KT1 is, write once more. KT1 is 1 by 1 minus XSN. XPB is binary system. 1 minus XSN liquid actually. This is XSN in the liquid phase. Okay. So XSN 1 minus XSN times PO2 power half. PO2 power half. So KT1 is 1 minus XSN. You write here in case there is any doubt. Liquid, and then give a bracket here. No problem. XSN liquid. This is your equation for the curve AB. So this represents, okay, call it equation 3. Call it equation 3. 1, 2 already there. 3. So equation 3 is represented by equation 3. You remove this, okay, this is unnecessary. This equation 3 right here. Equation 3 is represented by what curve? AB. Remember, this is lead oxygen, lead oxide. Here lead oxide is there. Okay, this we have considered. What is the, for this curve, what is the relation between Xtin and what? PO2. Represented by curve AB. So you have got an equation. So equation is this, and easy, because how will you get this? How will you plot this yourself? For example, KT1 is known quantity. Delta T0. KT1 is a known quantity. So you can choose XSN, different values of XSN, and plot this against PO2. Okay, you see. So you get corresponding values PO2 and several set of XSN PO2, and then connect this. That is a standard practice. Then you generate the curve if you want to do yourself. So this is the represented by curve AB, and noting that just you should be actually confident about this, or you should be actually should be free from any confusion that or you should make sure that this equation is well represented by this curve. Okay, or apparently you can see this. Okay, or very easy check. Easy check is what? noting that as excession increases, what happens? Tell me. As excession increases, say follow this curve. Excession increases, what happens to PO2? PO2 increases. And see here, excession increases means whole thing is decreases. If it decreases, and this is the left hand side is a constant, so one term denominator, this term decreases, the other term will increase. So as excession, PO2 will increase, and it is satisfied by the curve. Okay, so it's okay. So one quick easy check is that it is satisfied. So one is done. So next is what we will take up next. The next equilibrium for this curve, BC curve. So similarly, we have to consider delta G02. Start similarly, delta G02 is what again in the form of A plus BT. And now we consider steam dioxide equilibrium for the purpose of finding the equation of BC, which involves steam dioxide solid. Okay, so so what happens? It is also A plus BT. Write this A plus BT. These are known quantities as before, and I am giving you exact values for this. Is what exact values? Minus 574882. Minus 574882 plus 198.4 T joule. Okay, this is the actual data. This is what we proceed in the same manner. Is minus R T ln K T. Which equation? This is the second equation. 2 KT2. Again, you know, you can write this. T is known, R is known. So such thing, this leads to KT2 being known quantity is known is what? Write the expression correctly. ASNO2 solid over ASN liquid. ASN liquid, impure liquid, you understand it is part of lead tin alloy. Okay, like here, this is also impure, but it was highly enriched in lead. Okay, high concentration of lead. So it is XPB we have written. We have not written 1. Okay, it is very close to 1, but it is not exactly 1. So XPB we have maintained, and correspondingly 1 minus excession. The purpose of writing excession, I have said, see the equations are against PO2 versus excession for both curves. This is desired. When it is done, when they are found, they are done, then you have got the equations and you have got the stability diagram. So once you have got this, and you see they intersect here, and draw a horizontal line and complete the diagram. So I said, and then what we will write here? PO2. Okay. Again you write ASNO2 is you remember it is pure. So what you have, or you write what? KT2 is like this. KT2 is what? 1 by, oh no, this is not so easy. Activity of tin, what you will do? See, activity which tin is here, but tin, see, finally we want to reach, we are concentrating on point B, where excession is the same for both the curves. If this is our focus, this point you see what happens to excession. This is, see, excession is the value is what? 0.005 or thereabout. That means very dilute. Means there is a deviation. I'm sorry, I removed the card. Okay, this one very small. So this is route slope. This is a deviation. So what it will introduce, what it will invoke, it is what? Tell me what is the activity? Activity of B is gamma B 0 XP, because 0 it is very tending to 0 concentration of the dilute solution. dilute solution of tin inlet. This domain, this domain, this domain. See here, around this, it is a dilute solution of tin inlet in this domain. Okay. So dilute solution, what is the equation? Gamma B0 XP. So it will be also gamma tin 0 XSN. XSN liquid, you should write here also. I guess it is better you write here. Liquid and PO2. PO2. Okay, happy? Now gamma tin 0, as this gamma is a function of, I told you, temperature. Gamma value changes with composition, temperature, like this. So gamma tin 0 value I have taken. I actually didn't refer to the data book, okay, but I have considered 10 to the power minus 5. Assumed, okay. So it would be better. It is better that if we put in the correct value, exact value, data value, but gamma tin 0 actually, I actually consider some value just for illustration purpose. So at this temperature, obviously, gamma is a function of temperature, okay. Now you change the temperature, gradually moves towards, increase the temperature towards the Raoult's law. So gamma changes. So for this temperature assumed, gamma tin 0 is assumed for T is what temperature? 1023 Kelvin. Assumed, okay. It is not exact value. I have not used, perhaps I didn't actually take trouble to find the exact data, but no problem, but we will understand. So given this, what it means actually, if you have this, then again, what is that? That is, this is 81, okay, previously, okay, very good. So this is 3, third, this is fourth equation. This is again XSN versus PO2 relationship. XSN liquid, this is XSN liquid actually, yeah? Liquid. In the liquid melt. Okay. Tin oxide dioxide is pure. PBO is a pure, no problem. Only in the liquid phase. Liquid phase made of lead and tin alloy. This is pure lead, pure tin, and lead tin alloy actually works between these two. So what is, assume no problem, but don't worry about this third and fourth. So this is equation for this represents which equation? This is XSN versus PO2. XSN versus PO2 for the curve BC involving tin dioxide. Okay, this one, so BC. So you write similarly equation 4. Equation 4 is represented by curve. Which curve? Which can be BC or CB, you may call it CB. Okay, CB. Noting that again, you note just a simple check. If we increase XSN, XSN increase this way for this curve. Concentrate on the BC curve BC. It's okay. Concentrate on curve BC. If XSN increases, PO2 decreases. So see what you see here. As XSN increases, PO2 decreases because left hand side is a constant, 83 is a constant. So if one term in the denominator increases, other term must decrease. So it is increasing. So it satisfies as noting that as XSN increases, PO2 decreases. And here what you have? XSN increases, PO2 increases. XSN increases, PO2 increases. Here XSN increases, PO2 decreases. So So for two curves, major part is over. I am removing this again. Major part is over. So what you will do then? Okay. Now you want to solve this. Solve these two curves for point B. Point B has a PO2 value. I am giving the answer is 2.26 times 10 to the power minus 12 atmosphere. And what is the excitation? 0.005. Imagine 0.005. This is, but solve for this. How you solve? So get excitation from either relation and then equate them. Then you will get answer. So proceed. So from 1, 2, 3, from 3 and from 4. From 3, equation 3. Excitation is what? Excitation is what? Tell me. Is 1 minus, take a look. 1 minus 1 by KT1 times PO2 powered half. And from equation 4, right here, from equation 4, what is excitation? There is a excitation liquid, you may write. Excitation liquid, what it is? Tell me. 1 over KT2 times PO2. So get 2, and here actually this is this, and they will intersect. They will meet at a point, namely point B, when these two excisions are same. That means the equality of excision refers to point B. Solve for excision by equating these two. That will give rise to the excision for point B, where they meet, where they intersect. So do that. So or hence corresponding to point B, at which two curves meet, what we have, hence corresponding to B at which two curves meet, what we have, they are equal, right? 1 minus 1 by KT1, meet means excitation is same, so equate this KT1 PO2 power half is 1 over KT2 PO2. That's right, no problem. This is okay. Or you write here, okay. Okay, this is actually or 1 by I think you don't. I'm sorry. Okay. I think I'm removing this part. That's first top 2 lines. I'm removing this. Okay. Yes. So give a star here. Star here. Star here. You write. So what you are writing? Write this. Or 1 by KT1 PO2 power half plus 1 by KT2 PO2 is 1. Okay, is 1. Okay. Or what you have, just add these two. You have KT1 KT2 times PO2. In the numerator you have KT2 so there is a 10 to the power minus 5, perhaps I have ignored. Oh, I have removed this. There was a 10 to the power 5 here. There was 10 to the power minus 5 here. Okay, I am very sorry. Yes, I have removed this. It was what is the relation was? It was what? External liquid. I am writing for you. External liquid. This was there. External liquid is what? 1 by 10 to the power minus 5. That is the gamma tin 0 times KT2 times PO2. From which you get this? X thing is 1 minus KT2 PO2 I have written. I have dropped by mistake. It should be 10 to the power minus 5 KT2. Please check this PO2. Okay. So if you write this, correct this. So then 1 minus this one is there is a 10 to the power minus 5 here. KT2 PO2. So you have it 10 to the power minus 5 at the beginning. 10 to the power minus 5. Then if you divide by this, okay, you have a 10 to the power minus 5, of course. Oh, what is the other one? Is one. Then you correct this KT2 10 to the power minus 5 KT2 PO2 this one. Okay, PO2 they together is 1 side change. Also this is the denominator. Then you have got 10 to the power minus 5 and KT2, and this is PO2 and this is PO2 power, so PO2 power half. You will get this plus what you will get here 10 to the power minus 5 is okay, KT2 is okay, KT1 only. Yes, right, KT1 alone, KT1 is 1. Or what you get, write this 10 to the power minus 5 KT1 KT2 PO2, and this goes to this side and this take to the right hand side. 10 to the power minus 5 KT2 PO2 power half, then you take this minus KT1 is 0. Is 0. You remove this. This part is over. This part is over. Okay? Is 0. So this is a quadratic. Remember, note, you have not forgotten, I believe, note KT1, KT2 are all known quantities from delta G0 for these two. Okay, delta G data I have given you. So KT1, KT2 they are known quantities. So then what is the only unknown? PO2. And this is a quadratic relation in terms of PO2 power half, square root of PO2. Quadratic in terms of PO2 power half. So to solve this quadratic equation, you get the value of PO2 power half. PO2 powered half, from which you will get PO2, which you want to find out. PO2 corresponding to B means this value, 2.26 times 10 to the power minus 12 atmosphere. I ask you, I will tell you the data I have correctly taken. When we finish this, then I will say if there is any scope of uncertainty about this, that is actually where gamma Sn 0, that 10 to the power minus 5 that I have considered. Maybe I consulted some data, maybe, but this is some where you can have some changes, and accordingly the result will change. Anyway, note, first of all, note KT1 and KT2 are both known quantities. Okay. KT2 are known quantities. Unknown quantities, okay, obtained from delta G0 data, okay, obtained from delta G0 here, 1, I am giving you the data, and delta G0, 2. This you know, but still I wrote this, okay, remove this line. Okay, remove this line. You don't need, okay. So what you write here, then this is a purely a quadratic equation. This is a quadratic equation in this is a quadratic equation of PO2 power half. So you can solve because you know everything. So PO2 power half you can find out is known, that leads to PO2 is known. Okay, you remove this. Remove this. So PO2 is known, and that is one important. You have drawn already the curves, but where the intersect you have figured out also this value. What is this value? It is PO2 is Hacha. So so right here. Okay. Once you follow this, once the PO2 is known for point B, what is the corresponding XSN? PO2, this value 2.26 times 10 to the power minus 12. I will write this 2.26 times 10 to the power minus 12. Very small quantity. 10 to the power minus 12 atmosphere. That is PO2. 1 y-axis value. And x-axis is XSN. What is the XSN? Once the PO2 is known, XSN is obtained from where? See, XSN, you have two equations here. This is one, okay, XSN liquid. You are interested, very much interested to know XSN also, obtained from this 1 by, right, once more, 10 to the power minus 5 Kt2 times PO2. Or you can write from this also, either from this or from this, because they are equal. So can I remove this? Okay, very good, very good. So this is, so excitation, and this is Q2 is known, Kt2 is known, okay. So both are known. So giving this, both are known, these values I am giving you. The actual, these values are the coordinates of what? Of point B. Point B. After calculation, they are found as, this is important, PO2 is how much? As I have written, 2.26 times 10 to the power minus 12 atmosphere, and excitation is how much? As I have already shown here, 0.005. So the line that I have, horizontal line that I have drawn through point B is actually, that represents this PO2, constant PO2 value, okay, 2.26, okay. So this, now another story, once you have figured out, then you take a practical problem. So this is actually related to, this stability diagram is related to softening of lead. Means, how do you soften lead? By removing tin from lead, and try to remove tin as much as possible, so that lead is softened. Tin hardens it. So given this, so you want to, so suppose you follow me. Suppose here this is your initial alloy, lead tin alloy. Your job is to soften it, means remove tin from this. For this, how do you do this? By oxidation, by passing oxygen. Okay, so oxygen, but this oxygen, you oxygen, but this you have to stop. So then, see, you input oxygen, what is the mechanism? You pass pure oxygen. You don't make this oxygen. So it's difficult to make 10 to the minus 12, but you don't have to pass oxygen. But when it leaves the reactor, then it reacts fast to attain equilibrium, and the equilibrium values are actually given by this. These are the values, and correspondingly X10 is gradually, this direction gradually decreases, and lead is softened. So this way, this is moving how? Tell me, starting with this, as you blow with oxygen, I have written the control oxidation, they say. Why control? You have to stop. That is, when the maximum value is obtained, then you have to stop. And when you will, I tell you what, there's an indication that you are overblowing, or you are ruining the treatment. Follow, start. Then you blow oxygen, and oxygen, pure oxygen, but it leaves actually low pressure, because through reaction. So leads to pressure, and the values are actually in this vicinity, between this and this, in this vicinity. So what is happening? The result is tin is removed. Tin dioxide forms. Note that lead oxide has not formed yet. Only tin. It is unlike iron manganese system, where FeO, MnO, when FeO forms, MnO also forms, because they are in solid solution or liquid solution. But here tin dioxide and lead oxide are pure, they have no solubility. So tin dioxide pure is produced. And you continue because tin is actually removed to this point and you are happy, you are satisfied, your purpose is, but you will not stop, keep on blowing, then it will move further, tin is further removed, see, you may see here, tin here, value decreases, a time will come and tin dioxide is separated, tin is removed, where, in which form, tin dioxide, solid, separated, and liquid is becoming more and more enriched with lead, or more and more deficient with tin, which is your objective, objective, or your desired thing. So move, and time will come when it is here. When it is here, you have reached the climax. This is the maximum removal of tin, that is, tin content in the lead is 0.005. Suppose, for example, it was 0.1. Starting alloy is 0.1 mole fraction tin, 10 mole percent tin, or 0.1 value. So 0.1 reduces to, through both blowing, 0.005. Don't expect anymore. If you expect, over expect, then what will happen? If you still blow, then it will form. Then this is actually the time for lead to also oxidize. Not only tin, if you further oxidize this, lead oxide is also, lead oxide will, tin oxide is produced, and lead oxide, see here, lead oxide is also this curve actually, this lead oxide will start forming, lead starts oxidizing, which is undesirable. You don't want to ruin lead, you don't want to remove lead, you want to remove tin. So beyond this point, keep on oxidizing, lead oxide, see, lead oxide, tin oxide on, not only tin dioxide, and liquid here composition actually, see, it is here actually, this is the maximum removal of tin actually, see, you cannot have, this is the maximum, this is the limit, okay, it cannot be lesser, because it cannot extend this here, okay. So what will happen? Lead, then it is actually the time for lead oxide formation as well as tin dioxide. So you have to stop here. So how will you detect this one point? You all the time you watch for lead oxide formation. The moment lead oxide starts coming out, means you have to stop. Your job is done, and you have to be satisfied with whatever tin has been removed. That is the maximum, and that is in this case 0.005. If you say you have done this calculation quantitatively, you said report quantitatively, but are you sure your calculations are all correct? Calculations are, I would say, almost correct. Only one snag, one difficulty, that gamma tin 0 is an assumed value of 10 to the power minus 5. That is to be corrected, and if you correct this, then you will get this value even more precisely, okay, even more accurately you will get this value. But this is the procedure. This is actually, so this is okay, fine, very good. This is actually, we have completed this. So note, I am writing you for you only one assumption, one weakness of this, okay. So note, temperature I have chosen 750, no problem, 750 degrees centigrade, 1023 Kelvin, it can be 1050 Kelvin also, it can be 1000 Kelvin also, no problem, okay. So it should be a okay, melting point of lead and tin both, okay, they are low melting anyway. Not only one assumption, what is that? Gamma tin 0 is, sorry, gamma tin 0, how much? 10 to the minus 5 has been made in these calculations. The delta D0 data that I gave, they are perfect. It's all correct. Only gamma tin 0 actually, I have considered this value. Okay. this 10 to the power minus 5. So this is actually this is an assumed value. So if you get a exact value, then you just replace that 10 to the, suppose it is 10 to the power minus 3 say. So just replace by 10 to the power minus 5. So it will be actually here actually can see you get this answer. So okay. So you correct this. Okay, you increase the accuracy of this. Okay, precision will be better. Okay, thank you. So, but anyway, now some comments here I must write. Since this is actually all done, can I remove this? I'm removing this, huh? I'm removing this, just one or two. See, here I have to write this. Comment. Point B, I have already stated, but still it is better to note down. Point B denotes the lowest mole percent in the lowest mole percent in that is the maximum removal of tin from liquid lead from an initial lead tin alloy with the composition what is the composition? Tell me. With the composition X10 is how much? What is the initial? The way I have shown X1 as it X1. Okay, you just assure her she could get through. With the composition XSN is what? This is static. But your target is maximum value of removal or decreasing as much as possible. Lowering tin as much as possible to what value? Point D, which according to our calculation with some assumed value of gamma tin 0 is what value? 0.005. Okay. So with the maybe this, you can check this. Maybe I am not sure. Maybe may not be okay, very bad. Okay, may not be very unfair. Maybe close also. So check this. Okay, for the time. But I say as I don't remember actually. So exact, but you may be correct also. Okay. So anyway, with the you may be correct also. Okay. So with the composition X10 is what? What is the starting? X1. Starting maybe 0.1 mole fraction, 0.1, 0.15, 0.05. This has gone down to 0.005. Okay. X10 is X1. Okay. X10 is X1. Say X10 is X1. Say X is X1. Say in the maximum in a softening treatment of lead by control oxidation. control oxidation means you have to, LD blowing is also a control oxidation. You are blowing, so if you blow independently, all iron will be slag. Liquid steel will be slag. Independently if you blow. Control means you stop after say 35 minutes. When you have actually found the composition are actually agreeable or as per the specification. You have attained the specification, then you stop. So carbon say 0.001, manganese 0.5, okay, sulfur 0.002, etc. Phosphorus likewise. So this is the case. So you have to stop there. You have to stop there. Again, similar approach. In LD, you are blowing oxygen, pure oxygen. Blow from the top in LD. Also OBN from the bottom. Pure oxygen. But under pure oxygen, if you see pure oxygen, see here you can see the same thing. See, if it is one atmosphere, what is the equilibrium state? See, this is one confusion, great confusion. This is the equilibrium diagram. So one atmosphere you are blowing for softening treatment, control oxidation. One atmosphere oxygen you are blowing, that is the input. What is the output? The equilibrium value. That is reduced down to somewhere here. These small quantities. Same happens in LD. Blow pure oxygen, when it leaves, it 10 to the power minus 8 minus 10 to the power minus 10, 10 to the power minus 12. So reduced to that value. And the other gas is CO gas produced. Carbon in the alloy, in the steel bath, carbon and CO gas. And what makes up there? What makes up the total pressure? Because the open atmosphere, it is open atmosphere, here also open atmosphere. The balance was actually, the CO gas, the produced gas, that is. Here also maybe actually then you have to blow it actually. If it is a air blow, the nitrogen will make up, etc., etc. Or you can add some argon also, so that make up this, okay. But the idea is this, see, if you see the fallacy, you say it is equilibrium diagram and you are passing 1 atmosphere oxygen. So 1 atmosphere means here, way above here, you are all oxide. No PB at all. Let alone softening. No PB. Who will be softened? This is all lead oxide. But you are not equilibrating with 1 atmosphere oxygen. See, inlet is 1 atmosphere oxygen, that is in non-equilibrium, react and remove the lead plus oxygen is lead oxide, react and reduces dramatically to a very small value. That is small value, like in this vicinity. No problem. But what is the job? It actually removes initially removes tin dioxide. Tin, oxidized tin and separates it as tin dioxide, and liquid is more enriched with lead. And with the progress of the repetition of the same thing, lead is becoming more and more enriched and become more and more deficient with tin and becomes more and more softened. You continue, but you will be stopped. That is controlled. Control means when it will be here, pass the cell, repeat this. You cannot hope to pass this oxygen atmosphere. This partial pressure of oxygen, it is difficult to prepare. This is impractical. That is possible by another equilibrium, okay, say MnO, etc., by CCO, etc., but that is ruled out. That will make the situation more complex. You will not pass this. You will pass oxygen, pure oxygen. That makes kinetics also favorable, and the thing is, this oxygen is reduced strongly, readily to low values, 10 to the power minus 12 atmosphere, etc. Continue. That is the meaning of control oxidation. It is not that you control the oxygen pressure there. Because it's difficult to prepare. But this is very practical. This is everywhere you are doing. Copper making also same thing. Copper sulfide, that white metal copper sulfide. First it was matte, copper sulfide plus iron sulfide. Then it became, after removal of APS, it became purely copper sulfide, not copper yet. This copper sulfide is blown. When it blows, is again oxygen. Then it blows it into copper, but passing oxygen. But actually, it will continue. You understand what is the equilibrium state? Continue, then you will copper oxide. Copper oxide will form. Here you continue with don't control. Continue, you will have lead oxide and tin dioxide. That is equilibrium state. But that equilibrium is not your desired equilibrium. Okay, you don't want to equilibrate with. You equilibrate with this pressure. And remember, equilibrium should be considered at the excitant, when the reaction have taken place, not before the reaction. You pass, reaction takes place, and reaction attains equilibrium and leaves, the gas leaves, exits. So equilibrium should be considered at that moment, at the exit point, because that gas is in equilibrium with the reactants and products, the exiting gas, slag, metal, etc. So careful about this. So the sovereignty of lead by controlled oxidation. By controlled oxidation at, mention the temperature, at 1023 Kelvin. Okay, at 1023 Kelvin, what happened? Very good, very good. I would like to, one important announcement here. I would like to, very important, I would like to acknowledge that the outline of figure 6 means this figure. The final figure, stability diagram, outline of figure 6 was first proposed by one of my most brilliant students, is named, I am coming to this, his name is Biswarup Sinha Roy. Biswarup Sinha Roy, okay, he first actually proposed this Biswarup Sinha Roy back in 1998 at the Department of Metallurgical Materials Engineering Jadavpur University at Jadavpur University India. Okay. Here bracket here, okay. So he first actually in a test, in a class test, actually I gave a problem regarding this. Just I'm briefly giving you that episode or that incident. Is this? I give a question. I set a question dealing with sharpening of lead. This removal of lead. There are actually many students calculated correctly, but Biswarup Sinha Roy, he actually not only calculated correctly, but also he ventured into drawing this diagram. That was totally new. These actually, I tell you one thing, this you will not get in any book. No book. Up till now. As of now, no book. This was first, he actually sketched this form that actually inspired me. That inspired me into developing the whole thing, these calculations, all these things. Then I developed this, no doubt. But he actually he's the inspirer. He was the inspirer. My student inspired me into thinking more about this. And I was so much, okay, impressed with him. Okay. And I am very much grateful. I acknowledge him as his contribution. So that's why I mentioned him today. Very one of the most brilliant students of our department. And okay, so anyway, this is in passing you may note this. So lastly, I want to tell you, it is interesting to note. Actually, do you see any resemblance of this figure with anything else already? For example, in the FeO-MnO system, FeO-MnO system, what it resembles, what that diagram look like an isomorphous system, binary isomorphous system. Complete liquid solubility and complete solid solubility. This I said. Here also there is some similarity with some well-known diagram, binary phase diagram, like inverted eutectic diagram. Have you noticed this? Very interesting. This is like inverted eutectic diagram. So this is, let me pin. It is interesting. that figure 6 has the same look as an inverted binary eutectic phase diagram. With this, we have completed 6 examples: construction of stability diagrams and associated discussion. 6 examples. This was the 6th, the last, and we have completed this. We'll take up next assignment number 13. That will deal with problems involving Gibbs Phase Rule, demonstration of Gibbs Phase Rule, of the Gibbs demonstration of the Gibbs Phase Rule, and also construction of stability diagram. Okay, so this is assignment number 13. So this is over. So let me based on based on the Gibbs Phase Rule and stability diagram, that is assignment 13. So it is time for. So I am removing all this. All this I have to remove. So start construction of stability. Actually, let me check if I actually can. So we will now take up the next thing, that is the assignment 13, in which we will actually consider several Gibbs Phase Rule problems as well as construction of stability diagram. Okay, very good. Good, very good. Let us start. So, what is this? Assignment number 13. Okay. So what is this? 5 problems we will discuss. 5 problems. Based on the Gibbs Phase Rule and stability diagram construction and the stability diagrams Very good. This is assignment number 13. Problem 1 to the start. Just remember 5 problems. So problem 1, first problem, what is this? This, I tell you what, this is actually dealing, I outline the problem, it is segregation, roasting of copper, when producing copper from copper oxide. Segregation roasting or segregation, simply segregation of copper with the help of, from copper oxide, with the help of sodium chloride, salt, and carbon, the reducing agent. So these are the 4 ingredients that we will add actually. So on the reactant side, and moisture to produce actually carbon monoxide, hydrogen, etc. But this is a complicated reaction. So we will make a phase rule analysis of this. That is finding the degrees of freedom, and to show how by specifying the degrees of freedom we will be able to define the state of the system at equilibrium. Everything okay? Define the state of the, as we have done. So, but this is the only thing is that this is a very practical and very complicated. A number of reactions are involved. So not very difficult. You have done number of problems, number of times, etc. So let us start. The segregation of copper Let me write the problem first. The segregation of copper from copper oxide treated with a mixture of sodium chloride. So let us write this segregation of copper. Sodium chloride and coal in presence of, coal means carbon, in presence of moisture. In presence of moisture can be represented as represented by the following overall reaction. By the following overall reaction. CO2 solid plus NaCl solid plus H2O vapor, moisture, vapor plus carbon means coal, solid, it goes to, I have not balanced it, not necessary to balance also, don't worry. I will balance where it is required, you will see this. Plus just outline of the reaction is what? A schematic, Na2O, because number of components and number of phases are required to find the degrees of freedom. And when you apply, then individual reactions must be written, okay, and in a balanced state. That will do also. But overall, Na2O solid, this is a product. Copper, obviously the desired product. Main thing is copper. This is a copper making, alternative copper making, the dry condition, not molten copper, plus copper solid, plus CuCl3 vapor, plus Cu3Cl3 in the vapor state, plus HCl, plus HCl gas, plus CO gas, plus hydrogen gas. These are the thing that is okay. The different phases which are in equilibrium, in closed system operation, are shown in figure 1. Are shown in figure 1. Okay, very good. What is the figure 1 like? This is just a box closed system as it should be. Okay, I'm doing one thing. Full system operation, so maybe constant pressure. Okay, I'm giving you. Actually, beforehand I should not mention. Okay? This you can modify later. This is a closed system, a container. It can be constant. It looks like constant volume, but you can always make it constant pressure by, as I have already told you, there are many ways: open reactor or cylinder piston type arrangement. Constant pressure you have done number of times. But why constant? Since I have not explained why constancy of pressure comes, so that's why I am not showing this. That's a box, container, closed system. Currently it is constant volume closed system. Very good. And of course, thermal, constant temperature, very easy, okay, temperature controller, etc. So this is no problem, but this I will take up. Okay, variables I will not touch now. But the reactions, what are these? Right lines, please. CO2 solid, NaCl solid. Like this, copy this. First carbon solid and Na2O solid and copper solid. It's all solids over. Then what are the gases? Gases are H2O, vapor plus, then what you have? CO3Cl3. Then you have what? HCl. Then you have CO. These are all gas. Okay. COH2. HCl gas, CH2 gas, and CO gas, etc. This is what you will see right figure 1 as it should be. This is your closed system. So now the problem question is this: make a phase rule analysis of the equilibrated system, of the equilibrium system. This is a general question. Make a phase rule analysis. General question. But specifically, what I should write? Specifically, that is, what is phase rule analysis? Just find the degrees of freedom. Find the degrees of freedom and then show how the value of degrees of freedom means F. Find the value of F, the degrees of freedom, and then show how by fixing a number of variables the state of the system can be at equilibrium can be fully defined, fully described. That is, first find out F. F, that is the freedom. Find out F and then demonstrate how by fixing a number of variables the state of the system can be fully described, fully specified. This is the total question. This is the question. Okay, solution. So take up solution. Solution. We start with this. F is C minus P plus 2. F is C minus P plus 2. Now what is the C here? Number of components is 6. Number of phases 6 plus 2. Why these are 2? Explain this, explain. Complete this. Is how much? 2. Explain. C is what? 6. Why? Right? What are the elements? Go by number of elements. Okay. C is number of elements. What are they? 6 here. What are they? Tell me. Copper, oxygen, sodium, chlorine, hydrogen, and oxygen. We have given this. Copper, oxygen, sodium, chlorine. Okay. Copper, oxygen, sodium, chlorine. Okay, very good. Carbon have I given? I am not giving carbon. No? I will include carbon also. Carbon, chlorine, hydrogen. So 6. We write here another thing. Remember, this is important in this case. Number of ways to get the 2 ways at least, 2 principal ways to find C. One is number of elements, very easy. Another is number of species minus number of independent reactions. And both ways you will get the same result, and then it is very satisfying. You are all set. But if you don't get the number of independent reactions difficult for some reasons, then you will do one thing. You find C from number of elements. And that is perfect answer. You got the answer. Then you use that value now to walk back to find the number of independent reactions by using the other formula for C. What is that? Is nothing but number of species recall number of species minus number of independent reaction equilibria. Recall this. You recall this? What is the number of species? No, not yet. Now species how many? That is very easy for you. 1, 2, 3, 4. 5, 6, 7, 8, 9, 10. 10 is the number of species. So 10 minus number of reaction equilibria. Number of reaction equilibria. What does signify? What does it signify is hence number of reaction equilibria is what? How many reaction equilibria here? Independent, right? Independent. Number of independent reaction equilibria. So number of, right, okay, number of independent reaction equilibria. How many? Tell me. Now make use of this value of C in this relationship to find out the number of independent reaction equilibria is nothing but 10 minus 6 is 4. Very useful, very useful. You have 4 independent. Which are they is not important. Any 4. Right, you can write only 4 out of this. You cannot. But if you can write more than 4, then one of them, say 5 you have written, then one of them has been dependent and constructed out of this 4 by addition, subtraction, etc. So you have written 7, means 3 you have extra written by manipulating this 4. But which 4 is independent? Never. Concept clear. Make concept clear. Any 4. Number is more important than who is there. Any 4, then others are dependent. So I'll write, of course, you write conveniently your 4, the 4 independent, simple type. Actually, I always recommend, or it is normally recommended, you write the simple type, like formation type, if available. Okay? Simple type. Okay? So that you do. But you have got a very interesting information, useful, very useful, that number of independent reaction equilibria, which will be written is 4. So this is one C. C is 6. Explanation here. C is 6. P is what? Number of phases. P is what? Number of phases, right? Number of phases. How many? Tell me how many phases here? See here clearly. 1 solid, sodium chloride solid. 5 solid. Copper oxide, sodium chloride, carbon, sodium oxide, copper, they are all pure. Means don't form solution. So they are separate, pure. So 6. So 1, 2, 3, 4, 5 solid, and gases are all miscible and form one phase. So 6. 6 here, 6. What are these, right? How do you get these 6? 5 solids, right here. 5 solids. Which are they? 5 solids. Which are they? 5 solids. Which are they? Right nicely. Cu2O, right? Sodium chloride. Oh, wait a minute. This is disturbing, very much disturbing. Cu2O, right nicely, NaCl, then write carbon, 5 solids, 5. Carbon, then sodium oxide, then what? Copper. So 5 solids. Last, why it is 6? Plus 1 gas phase. What is that gas phase? Constituents are, right? H2O, CO3, Cl3, vapors, same as gas, HCl, then CO, hydrogen. So 5 species are there in gas phase. 5 species are there in gas phase. H2O, CO3, Cl3, HCl, CO, H2. So degrees of freedom you have obtained 2. Which you will choose? Now which you? We are not drawing stability diagram. We are not drawing stability diagram. So a max, not that. Here we are finding F, and so demonstrate the phase rule. So first F, then you will choose conveniently. Your anything you can choose, but normally you choose temperature in the total pressure. Total pressure, right? Total pressure. You know this total pressure of the system. This is temperature. So if you want to, since I have now mentioned this temperature, total pressure, you can make this system an isothermal and constant pressure system. How? Isothermal is you give a, here you give actually what is that called? Thermostat or temperature controller. Yeah, like this. And pressure, how maintain pressure? Cylinder piston arrangement. Okay, cylinder piston. I am showing you. This is thermostated, or you may, if it is a open reactor in a furnace, then it is a temperature controller. So thermostat, temperature, it is fixing temperature. Say temperature, you are fixing, 1000 Kelvin per hour, 1200 Kelvin per hour, and if you are, since you now extend this, just like a cylinder piston arrangement, fixed pressure. Pressure you fix that. Or open atmosphere, it is also fixed pressure. Open atmosphere, 1 atmosphere. If you would want to do it less than 1, then what you will do? Vacuum system. More than 1, compressor you will use, compressed system. You know this. So idea is this. This is actually the phase rule analysis today. Concentrate on phase rule analysis. 2. So you see, with just two, you fully define the system at equilibrium. Means what? You will be able to give the partial pressure of this all species of full definition. Partial pressures of the gas species. So this you get. Let us see how you get this. So 4 equations independent equilibrium. So write this one by one. 1. 4 independent reaction equilibrium. Write this. First, twice NaCl solid plus H2O vapor is Na2O solid plus 2HCl gas. This is, from this you get what? KT1. KT is known, temperature is known, for the delta G0 and KT is known. What is the expression for this? Write nicely. Activity of Na2O solid PHCl squared, activity of NaCl solid squared pH2O. Okay, at equilibrium. Come slowly. Don't touch. It's okay. So this is actually, this is the equilibrium constant expression, and you have the so this is equilibrium constant expression. So you have this, actually these are the solid and gas phases. So how much time left?
1 hour 45 minutes gone.
20 minutes.
15 to 20, 15 minutes left.
15 minutes left. Yes, that's okay. What is this activity? Pure 1. This is pure 1. So these are the expression. Only one equation. One equation. Yes. Call it. This is so useful. Call it equation 1. Okay. KT1. You see the way I have labeled here 1 this time. So you label accordingly. KT1. This is equation 1. Second equation is what? Na2O solid. Oh, sorry, Cu2O HCl. Okay, I'm sorry. Cu2O solid plus 2 HCl gas. Cu3Cl3 vapor 2/3 plus H2O vapor. This is KT2. This is what you write. Partial pressure, this vapor partial pressure of Cu3Cl3 squared 2/3 by partial pressure of H2O over activity of Cu2O solid over HCl squared. Okay, this is your second equation, but one simplification is that this is 1. So okay, two equations. Third equation. You consider this. Third, remember at equilibrium all possible reaction at equilibrium. All possible. When a system has attained equilibrium, all possible. Whatever you write, you manipulate this to write another one. So eliminate H2. So add this to. So for example, this is in equilibrium. This is in equilibrium. They add this to H2 cancel. So this plus this plus this, or this cancel also. This and this cancel also. This cancel. So this plus this is this plus this is also equilibrium. Because all species are at equilibrium with one another. That is, if it is not, then that is not complete equilibrium. That is called partial equilibrium. But here you have to consider, idealist, you have to consider that the reaction system has come to complete equilibrium. Kinetic has been fast and no problem. Moreover, we are actually accepting that if the system is given, if it is given that system is at equilibrium, then it is to know whether you can handle, you can apply it. We can apply it. Even when, if the system is under equilibrium, can you describe the system at equilibrium? Means all partial pressure. So this is the problem. So whether it is not, okay, I have explained this. So all possible reactions at equilibrium, that is a complete equilibrium. Given that complete equilibrium, you are using the phase rule. Okay, good. Third is what? As I told you, 2/3 UCl3 Cu3Cl3 plus H2 vapor. 2 Cu solid plus 2 HCl. Oh, this is KT3. These are right. Activity of Cu solid square what is this value? 1. So this is your third equation corresponding to the third one. Okay. Fourth is what? Fourth is what? Fourth, tell me, fourth is what? Carbon plus H2O. plus H2O gas is CO gas plus hydrogen. KT4 is what? PCO, P hydrogen, activity of carbon, PH2O. So this is your 4 and this is 1. Okay. So 4 equations. These we have chosen. Independent. These are all mutually independent. No one can be obtained from combination of others. For any combination of others, you cannot get any one of them. Means they are mutually independent. For example, I am showing, if you write, as I told you, you add 1 and 2. Add 1 and 2, see what happens. Add 1 to H2 cancel. And what your HCl, 2HCl cancel. What you get, I am writing graph. 2 initial solid plus CO2 solid goes to Na2O solid plus 2/3 CO3 Cl3 vapor. See, this is another reaction. This is another just combination of this. Okay, no problem. So this cancels, very good. So this is balanced also. Have I used this? I have not used this. Okay. So this, if you write this, it will 5, but it is 4. It should be 4. Actually, this is meaningless. This is meaningless because you are actually generating this through the use of these two, of first and second, by adding. So this is an independent. This is a dependent one. Dependent reaction. And discarding. These are mutually independent. If you see this point, okay, see this point. So you can do one thing. If you want to include this as independent, do this, no problem. Then you are okay. Discard one of these two. Maybe this and this possible, or this and this possible. But don't have these and this together. So out. Out. So far 4 relations obtained involving which partial pressures? These gas phases. 1, 2, 3, 4, 5. 4 relation on partial pressures because solid, pure, condensed, one they are removed all gases. So these 5 gases are showing in different ways, in different combinations, different relations, 4 relations. But is it possible to solve 5 unknown from 4 equations? No. You need another relation to solve these 5 unknown. These are the unknown. 1, 2, 3, 4, 5 gas species. 5 partial pressures unknown. 4 relation. How will you be able? Now you have another. You might say temperature. Have you used the temperature? You have, of course. Temperature. Equilibrium constant is a function of temperature. You have used temperature. You got the delta G0 is minus RTL NK, from which you get KT. Similar KT1, KT2, KT3, KT. So you have already used temperature. Pressure you have not used it. Total pressure P. So P in 5th equation that I am writing. You careful. P is what? Sum of these partial pressures. All partial pressures. Keep on writing. PH2O plus right here PCU Cl3 plus PHCl plus PCO plus PCO plus P hydrogen. This is your fifth relation. 5 unknown, 5 relations, and they are solvable. they are now, they can be now solved, and you get the partial pressures. So you will get actually gas composition. Partial pressure over total pressure gives the mole fraction. The gas composition you get, and solids are pure, so their mole fractions are 1. So solids are known also, composition known, and temperature pressure known. Temperature pressure and composition of each phase. This is the purpose of the Gibbs phase rule. When you define the temperature, pressure and composition of each phase of the system, then you have completely defined the systematic rule. So let me write here. I'm removing this here. Here I am star mark. Star here. Take to top. So this is in nutshell. 5 unknown, 5 equations solved. Hence, so 5 unknowns star. So 5 unknowns, specify them pH2O, PCU3Cl3, specify PHCl, specify PCO, specify P hydrogen. 5 unknowns and 5 equations. What are the equations? 1, 2, 3, 4, 5. 1 to 5. 1 to 5. Hence these 5 unknowns are solvable. Hence, you remove this line. Solvable. Hence, with the help of two degrees of freedom, F goes to 5 minutes.
1 minute left.
It's okay. With the help of 1 minute or 1 or 2 minutes. With the help of 2 degrees of freedom, what are namely these two? You have to. I have removed this. F goes to what are the temperature and pressure I consider. So with the help of 2 degrees of freedom, the state of the system is fully defined. Is fully defined. In terms of fully defined means in terms of temperature, pressure and composition of each phase. Temperature, already we have fixed temperature T and P, temperature, pressure composition of each phase. Composition of each phase. Each phase means how many phases? 5 solid phases are there. Temperature, pressure known. Composition of each phase. 5 solid phases. They are pure. 5 solid phases. Are each pure. Hence, what is this? Xi is 1. For each case, 5. Mole fraction is 1. Pure. So that is composition is solid phases. Each one. Xi is 1. And 5 and 4. 5 gas phases and 5 gas phases. For 5 gas species, 1, 2, 3, 4, 5. 5 gas species. For 5 gas species, what is the mole fraction? Xi is Pi by Pi partial pressures. As you saw here, 5 partial pressures are 5 unknowns. We have said 5 unknowns. 5 unknowns are known. So partial pressure over total pressure. Partial pressure over total pressure. Partial is a mole fraction. Xi is Pi by P is known. So, if the partial pressure gives easily, if you know the partial pressures, you know the total pressure, you know the composition. And for solids, pure solids, mole fraction is 1. It is not to be emphasized. Okay? It is so common, so natural, so easy, so simple. So no problem. So anyway, formally speaking, temperature, pressure, and composition of each phase has been fully described. Is actually they are actually fully defined, fully described. Okay. So problem 1 is over. We'll take up problem 2 next class. Next class, problem 2 onwards. Remember, 5 problems will be there. So one of them is so far over. Okay. 4 remaining. We'll take up them. Okay. Thank you very much for your patience and for your interest and for your devotion. Okay. Okay. See you next class. Okay. For the time being, bye. Bye.